Hello, everyone. Welcome back. So just to kind of give you a glimpse at the future. This week we're going to be going over 1.5, which is the last section of Unit 1, which is on continuity. And then we'll be starting up Unit 2 with section 2.1, which is on the definition of the derivative. That will be part of Exam 1. So Exam 1 will cover Unit 1 and then 2.1, because I feel like 2.1, despite it being derivatives, which is going to be the next exam, it fits better with this material. So, and you'll see why when we get there. I'll be posting an exam review a little bit later, either today or maybe tomorrow. And usually the way I like to have my review guide set up is that there's a question prompt. So there's all the questions. And then there's the answer key on the back. Answer key just has the answers. And then later on in the week, I will add the solution guide, as long as I have it. Pretty sure I do. So the solutions are meant to be a situation where you look at those if you do not know how to proceed. When you're doing an exam review, you should be trying to do the problems yourself 100%. Looking back at the answer, and if you can't get the right answer, you should be trying to find out from someone else, or emailing me, or a classmate or whatever. And then if you truly can't figure it out, then that's when you want to look at the solution guide to see where the mistake's being made. But just looking at the solution guide is never enough. Watching a game of basketball doesn't make you any better at basketball, right? I mean, you might see some cool moves that people are doing, but unless you actually go out there and do it yourself, you're not going to become a better basketball player. So, yes.
Is there a view like similar to the past service in building blocks to help us deal with it?
Yes. This is a joke. But the thing is, my reviews are not like they're not a practice exam. They're meant to be an overarching concept. Like if you can do my review, you're in pretty good standing. The way I usually like to study, like the way I recommend studying, is studying your notes, looking over your old, like looking over some of the homework exercises, and then looking over old quizzes and stuff to see where mistakes were made. Then going over the review itself. And if you feel like you're not having too much of a challenge, that's usually a good thing. So that, like, it's not a practice test. All right. So did anybody get a chance to do this problem right here? You guys, the challenge problem.
Yes.
I'm going to give you a recommendation just so, because we got some ground to cover. The thing is to expand it. Now, I could have even been more chaotic and made this to the 40th power or something like that. The thing is, that's a polynomial. It's just a factored polynomial. It's 2x minus 3 to the 4th power, and it's factored form. But if you were to expand it, like, yes, you could go out and FOIL it out 4 times. You could. I wouldn't recommend it, because remember, all we're interested in is the highest degree term. When you're looking at limits at infinity, all you're looking for is the highest degree term. So what this is going to be is going to be 2x to the 4th plus a bunch of stuff over 3x to the 4th plus a bunch of stuff. Would you guys agree?
Yes.
Because when you FOIL this out, the first terms are always just going to get multiplied together. So you're just going to get 2x times 2x times 2x times 2x. And then there's just going to be a bunch of lower degree terms at the end of it. Similar here. I mean, yes, you could FOIL it out. It's not too terrible, but you don't care about any of those things because we're looking at the limit as x goes to infinity. So with that in mind, that's being an abusive of relation of notation here. So I'm just going to point to this thing right here. And so using that should help you figure out why the answer is 16/3. So we're going to talk about the tricky, also known as fun cases. And we're gonna be dealing with sometimes it's got rational functions, or polynomials in it, but it's, for the most part, it's got radicals. These are the functions that primarily that you will see, like the expressions that are inside these limits. These are the types of functions that end up having, these are the functions that end up having multiple horizontal, multiple horizontal asymptotes, 2 of them. So when you're dealing with this, we have to be careful though. So what this is saying, there's 2 important pieces to this part right here. This thing that's saying that the square root of x, the square root of x squared is equal to the absolute value of x. On one hand, it's telling you that if you have the square root of an x squared, it basically grows at the rate of x to the first power, right? Because I mean, like, what is just as a reminder, I think we wrote this down, but just as another reminder, the nth root of x to the m is equal to x to the m over n. Did we write that down before? I don't think we did. It's an important fact from algebra, is that the nth root of x to the m is equal to x to the m over n. A good way to memorize that, by the way, is the powers above, roots below, right? Roots grow below us, powers that are above us, just the power of math, right? More specifically, let's just that whole thing of the powers above us, whatever. But the power goes above, the root goes below. So if you have the square root of x squared, it's essentially acting like x to the first power. It grows at the same rate. That is the first observation. And the second observation is that it has to have the absolute value symbol here, because if we were to claim this, if we were to, like, don't write this down, but if we were to claim this, that would mean that this would have to be true for all x values, right? Because it's an equal sign. But I caution you, at x equals -5, right? If I plug in -5 for x, I get the square root of -5 squared equals -5. But the square root of -5 squared, that's the square root of 25, which is equal to 5. And so we would be saying that 5 is equal to -5, which is not true. So that is the problem. The absolute value sign is necessary because the square root always produces a positive value. So now, with that in mind, let's look at these examples. So the limit as x approaches positive infinity of 2x over the square root of x squared plus 2. Now, if you go way, way back, you'll remember that we can pull the limit onto the inside of functions. Remember that? As long as everything works out, right? As long as everything is nice and neat, things can be pulled in front. So the fact of the matter is, we could, like, we're not going to do it, but just as an aside, you could technically bring the limit onto the inside of this. I mean, I'm being a little hand wavy there. I'll admit I'm being a little hand wavy because technically speaking, the limit does not exist because it goes to infinity, right? But either way, it mostly works in this context. And the idea here is that this is taking the limit of a polynomial, right? So the rest of the stuff doesn't matter. All the smaller power stuff doesn't matter. The +2 is irrelevant when you're looking at the face of infinity. Infinity is so much larger than 2, it doesn't matter. So what we can do is just rewrite this as the limit, wrong color. The limit as x approaches positive infinity of 2x over the square root of x squared. We can just ignore the +2 because it doesn't matter at infinity. These will, like, the reason why I'm claiming that these two things are equal is because at infinity, they will be equal. And then what we know is that this is equal to the absolute value of x. So I'm going to add in an extra step here. This is the 2x over the absolute value of x. I'm going to add this step in. You don't have to, but I want to talk about it. Because John Doe student says, oh, well, I can just cancel the x's. But John Doe student is not correct, sadly. If only that were true. But the problem is that this is a factor of x. This is absolute value of x. They're not the same thing. At least not yet. They're not the same thing, so they can't cancel out. But what we do know is that as x goes to positive infinity, that absolute value sign is going to be redundant, right? Because you're taking the absolute value of a positive number. Every single time you get further and further out to the right, you're just taking absolute value of a positive number, and the absolute value sign doesn't matter there. The absolute value of 5 is still 5. Absolute value of 2 billion is 2 billion. So what we can write here is that as x goes to positive infinity, the absolute value sign is redundant. So this becomes the limit as x approaches positive infinity of 2x over x. Now we can cancel the x's, just like we were talking about when we were dealing with the absolute values. If the value is going to make your expression negative, you tack on a minus sign in front. If it keeps it positive, you just drop the absolute value sign. That's essentially taking the absolute value. Any questions on that? So then the x's cancel, and you just have the answer of 2. In stark contrast. Oh, Bill, you have a question?
Never mind, we'll get to that. Sorry.
For sure, because I think that the next one is probably what you're going to be asking about. This one, in stark contrast, is the exact same expression. Oh, I'm so sorry, I didn't see. The plus 2 in the radical. So that was one of the first things we took care of. The fact of the matter is because this is going to infinity, because we're blowing up, our x values are getting so large, that plus 2 doesn't matter. It's not like it exists, right? It's there, but as we get so large, that 2 doesn't matter. Like the difference between the infinity squared plus 2 is the same as infinity squared, essentially. Yes. Yes. At the very end, we're using the constant rule, because when the 2's cancel out, the x's cancel out, all we're left with is the limit as x approaches infinity of 2, which is going to be 2. And you can also understand that visually, because if you're looking at it as a limit, now you guys don't need to write this, but just to show you, if you're looking at the limits as x approaches positive infinity of 2, remember, this can be thought of as a function, f of x equals 2. That's the constant function 2, which is a horizontal line, right? And so as x goes to infinity, the y values tend to 2 always. And that's another reason why the constant rule works here. But I digress. So yes, we're using the constant rule to show that it's going to be 2. Now on the flip side with this one, we're going to do it the same. We're going to approach it the same way. Once again, the plus 2 doesn't matter. So let's actually add that. Thank you for Sarah, correct? Sarah brings up a good point. So let's mention that. The quote unquote plus 2 will not matter as x goes to positive infinity, so we can ignore it. We are only able to ignore this, once again, because this is going to positive infinity or negative infinity. Because the x value, I'll get to your question just a second. Because the x values are just going to keep getting larger and larger. And in the scope, infinity squared is just so much larger than 2, it doesn't matter. Yes, Charlie. It would not matter. Excellent question. Yeah, it does not matter whether it was 2 plus 2 minus 2, 2x minus 2x plus 5 billion x. because yes, 5 billion X is very, very large, but infinity is so much larger than 5 billion. Like you could just plug in 5 billion billion, right? And that would be, when you square that, it would be so much larger, it wouldn't matter. So as X goes to infinity, we can just ignore that piece of it. And it's, oh yes, Hector.
Would it matter if the +2 was outside of the square root and still in the denominator?
Great question. Great question. So Hector is asking, what if it was, instead of that, it was limit as X approaches positive infinity of 2X over the square root of X squared. And let's just, to save on simplification, like to make it a little more complicated, let's say there was something else out here like that. That is a good question. And it still will not matter because it's just a 5. If it was a 5x, because x squared, the square root of x squared grows at the same rate as x, that would become an issue. But as it stands, that +5 does not matter.
So the limit would still be 2 and not 2/5.
Yeah, exactly right. Because imagine as x goes to 5, like as x goes to infinity, it's like thinking 20 million bajillion fulfilling, whatever, banana fulfilling, whatever. This will just keep getting so much larger, and then you're just adding a little +5 at the end. It's negligible.
So kind of just, if it were in the numerator, it wouldn't matter.
Yeah, if it was in the numerator as well, it wouldn't matter.
Oh, it would.
Yeah, if this +5 was over here as well, still wouldn't matter. Yes.
It's like the same concept of getting the highest terms.
Yes. The highest terms are the only ones that matter at infinity. Nothing else matters besides the highest degree terms.
However, if it's a constant, you don't care.
Yes, if this was the limit as x approaches
These are
like
random.
7 or whatever, not that like this might give us a vertical asymptote. It won't, but this is where that 5 matters because it's local. Whereas at n behavior, when we're going out to infinity, we only really care about the highest degree powers. Charlie.
So it would only matter like the extra number that we had to have.
So it depends on the situation. But yes, like we want to be careful of it when it starts having variables as well. But at the end of the day, we're looking for the highest degree terms. So if it's a lower degree term, and in this case, the highest degree term is the first power. So the only thing that like the lower powers are just constant terms. But let's just, I think I have another example here. Yeah. I have an additional example that will help. But any lower power does not matter when you go to at infinity. Locally, it does matter. So here, when your x is going to 7, this one that I've drawn right here, here that +5 does matter because it's local. And we're talking about finite values. Whereas with infinity, we're talking about infinitely large values where everything else kind of just washes away. It's not important. Great questions, guys. This is like I remember when I was a wee mathematician having a hard time like the concept of infinity is a very, very hard thing for us to get to grasp as finite mortal beings. It is a very, very strange concept, especially because it brings up some of the weirdest things that you'll ever see. Just to kind of give you a little taste, just maybe kind of pique your interest into mathematics a little bit. There's a thing in mathematics called Gabriel's horn. It is a shape that you get by taking the curve 1/x and rotating it around the x-axis. You end up getting this this kind of funnel of this horn looking shape. So once again, you do not need to draw this. This is just to kind of pique your interest into mathematics a little bit. So you get this horn shape and you make it go on forever. This is an infinite horn. And because of infinity, because of the weirdness that infinity creates, this little horn, this shape, has finite volume, but infinite surface area, meaning that you could fill it with paint. You could dump it full of paint, but you could never paint the outside. It would take you infinity, like you would never be able to finish painting it, which is very, very counterintuitive, right? If you could fill it with paint, then you could just cover it with paint, right? But you can't, which is so strange. This is where the concept of infinity kind of starts to boil down and break apart for us. So interesting little counterexamples in mathematics. The concept of infinity is definitely a strange case, and I'm really glad you guys are asking all these questions about it. If you'd like to know more, infinity later on, please feel free to talk to me about it. But I want to do this one next. We're still dealing with the concept of infinity, but now we'll deal with this one. In the same fashion, this becomes the limit as x approaches negative infinity of 2x over the square root of x squared, the square root of x squared. And I'll point to this one too. The fact is that +2, as we go to negative infinity, it doesn't matter. And we can do this, by the way, also keep in mind that this is a square root and we're talking about a negative value. So we do need to be careful when we're talking about even roots, 4th roots, 6th roots, 2 millionth roots. Any of the even roots, you can't plug in negative numbers, right? You can't have the square root of -5. However, we're dealing with an x squared. So as x goes to negative infinity, that square will make it positive. So it is well defined. You'll see in the next problem where that issue arises. But we can do this because we're squaring that negative value, making it positive. So this becomes the limit as x approaches negative infinity of 2x over the absolute value of x, because the square root of x squared is the absolute value of x, as we talked about at the very beginning. But as x goes to negative infinity, I'm going to highlight that negative, the absolute value of x will equal negative x to counteract the negative. When you plug in a negative value, like if the inside becomes negative, when you plug in that value, you tack on a negative sign in front to counterbalance the fact that it would be negative, to ensure that the absolute value symbol does its job. Its job is to make anything negative positive. So this becomes the limit as x approaches negative infinity of 2x over negative x. The x's cancel, and this will become -2 by the constant rule once again. While you guys are finishing writing that, just this had me thinking about like when I mentioned the constant rule. One of the things I want to tell you about my exams, pretty much all my questions are free response on my exams, especially in calculus, are free response or not short answer, but like no justification needed. Like, you know how on that first quiz we had those limits and you just needed to write the answer. You didn't need to like show anywhere. You could just write 2 or 1 or whatever. So there's those types of questions, and then there's usually free response questions. So I'm never going to ask you what rule gave you this answer. So you don't need to know the name of the rule. You don't need to memorize like this is that, like we use the constant rule. And that reminded me to mention to you guys. So with the exam, you never need to ask me how many questions are going to be on it. It doesn't matter. I could give you a 1-question exam that will take 3 hours if I really wanted to. I try to, like, when I create my exams, I go through them very, very extensively. I try to make sure that I have the right amount of questions on there to make it doable within an hour and 20 minutes. And I try to make sure, well, an hour and 50 for us. I try to ensure that there's enough, like that it's short enough that you have time at the end to check your work. I've been teaching for 10 years now. I think most students finish with time to spare. So they can look over the exam and kind of review their answers. So don't worry about the number of questions. Just know that it is doable within the time allowed. Yes.
Sorry, I noticed something. When you're talking about constants, so the limit of x is approaching constant, we would care both about positive and negative when it's approaching by both sides. And
Okay, yeah, you go ahead.
that would get you like let's say, for example, we got 2 and -2, that wouldn't check out, and it wouldn't be correct, but when you talk about infinities, does that matter?
Yeah, you're not gonna need to worry about like left or right hand limit with infinity. There might be a very, very strange field of mathematics that look at left and right hands of infinity. I'm not sure. I haven't seen that. I do know, like, I think I told you guys that there are mathematicians who study different sizes of infinity. That is a field of mathematics, but I don't know if there's a field of like looking at infinity from the left and infinity from the right. I imagine you could do it, but either way. This one here, limit as z goes to positive infinity of the fourth root of z to the ninth plus z plus 2 over z squared minus 1. So, fourth root, so that's going to be one of the ones that we have to worry about. Third roots or whatever, you don't really need to worry about whether or not it would be positive or negative, because like the third root of -8 is -2. Third roots, fifth roots, 17th roots, all the odd roots exist for all numbers. So we don't need to worry about that at all. But point being, if we were to bring the limit on the inside, we'd see that we have the limit of a polynomial in here. So that plus z and that plus 2 do not matter since we're going to infinity. If we were going to a finite number, they would matter. But as it's going to positive infinity, that z plus 2 is going to be so small in comparison. Just look at the difference between 9 to the 9th power and 9 itself. Like 9 to the 9th power is, I do not know my my powers of 9 off the top of my head. So let me see here. 9 to the 9th is 387 million. 9 doesn't really matter in comparison. Adding 9 plus, so adding 11 to 387 million doesn't change anything. Relatively speaking, like imagine Jeff Bezos getting an additional $11. He doesn't care. That's nothing for him. That's worthless. So that's the same idea here. Anyways, so those things can just be dropped from the calculation. So only care about highest powers. So this becomes the limit as z approaches positive infinity of the fourth root of z to the 9th divided by z squared. That minus 1 doesn't matter either. That plus z and that plus 2 do not matter, and neither does that minus 1 because we're going to infinity. And so here, this is where we use that rule. The power goes above, the root goes below. So this is z to the 9/4. And then we say, oh no, Phil, how do we cancel z to the 9/4 and z to the 2nd power? It can't be done. It can't be done. No, it can't. So that's 2 over 1. You can rewrite the z to the 2nd power. This is z to the 8/4. Right? Because it's z squared. So writing it with a common denominator, you write it as 8/4, because that's 2. 8 divided by 4 is 2. And now we can take the difference of it and get that this is going to be the limit as z approaches positive infinity of z to the 1/4. Which you could rewrite again as the fourth root of z to the 1st power, but you don't need to. Any questions so far?
Can you explain again z to the 2nd power turns into z
To the 8.
over 4?
Yes. So the algebra that's going on here is, remember, there's one of the rules we know is the x to the a over x to the b. If you have the same base, then it becomes x to the a minus b. Top power minus the bottom power. So here it would be 9/4 minus 2. Now you can use your calculator if you want to do that. So so up here you get z to the 9/4 minus 2, but I'm going to rewrite that with a common denominator. So I multiply the 2 by 4/4. That's where I get the 8/4. Yeah, of course. So z to the 9/4 minus 8/4, which is where I get that z to the 1/4. Well, isn't this a fun case? It's unique, it's different than what we're used to seeing. It requires more work. So, no, did you have a question? So z to the 1/4, what will that go to as z goes to infinity? It's not a trick question. It'll go to infinity. It'll just keep blowing up. It takes a long time, right? Because the fourth root of 10,000 is just 10, right? So even going out 10,000 spaces on the x-axis, your only y value is 10, but eventually it will blow up to infinity. If you look at the curve, the fourth root curve looks like this. And it does increase. It increases slowly, but it does increase indefinitely. So, last one here. This one I deliberately, so this is why, especially when we're going to negative infinity, that's when we have to be very, very careful. We should be careful whenever we see a square root, an even root. As soon as we see an even root, we should make sure that it's going to get defined. Because as z goes to negative infinity, what happens here in the numerator? The inside of that radical, the inside of the radical will go to the negative infinity, making the whole thing not exist. So that's what we're going to write as, what color do you guys want? Pink. Amen. It's pink. I just saw the Barb movie again. Excellent movie. If you haven't seen it, you should. It's excellent. As z goes to negative infinity, z to the 9th plus z plus 2 will also go to negative infinity. Because you're going to get negative infinity to the 9th power. And a negative raised to a negative power, or sorry, a negative raised to an odd power becomes negative. Right? -1 to the 51st, -1. Very, very useful skill, by the way, is to know that the negative power raised to an odd power stays negative. Because you have an odd number of negatives. So the 9th root, not 9th root, the 4th root of z to the 9th plus z plus 2 does not exist as z goes to negative infinity. So the answer to this one is D and E. Okay. Any questions on that?
Repeat that one more time.
Sure. So because the inside of the radical will go to negative infinity, you be trying to, like, as you keep going out, you keep trying to take the 4th root of a negative number, which does not exist. So as z goes to negative infinity, that whole thing just doesn't exist. Plug in any z value past 0, past 1, or past -1, and it stops existing. As soon as you plug in -2, the inside doesn't exist. Any number after -1, the numerator will not exist.
Is it because on the graph on the left side, it just doesn't exist?
Exactly right, because you're trying to take the 4th root of a negative number, and the 4th root of any number, you like, unless you want to extend yourself to complex numbers, the 4th root doesn't exist. Just like the square root of -5 doesn't exist, the 4th root of -5 doesn't exist either. How does that look on Desmos? This function here? Off the top of my head, I do not know. We could easily graph it. Desmos is much faster at graphing it than I am. But it will not exist past -1. All right, these two. Let's see here. What time is it? I want to spend most of the time on continuity. So we will deal with these later. Fun problem. Very, very fun problem. But Notice that this isn't a rational expression, so it's not a power, like it's not. We'd be looking at infinity minus infinity, so that's going to be like we'll continue on later. And we'll start up with continuity. One of my favorite topics, and once you see what the definition is, you might like, well, let's actually just write it down. So a function f of x is said to be continuous at x equals a if the following three conditions are met. If any of these conditions is broken, if any one of these three conditions is not true, you do not have continuity. So the first one is that f of a exists. So in order for you to be continuous, you need the function to exist at that value. So we have to have a solid dot there. You need to have that the limit exists. You need to have that the limit exists. And last but not least, you need to have that the limit and the function agree at that value, so that the limit as x approaches a of f of x, so the limit of the function is equal to the function itself at that value. Now, just so this definition could be simplified to just the third point, because the third point is assuming the other two in it already, right? You can't claim that these two things are equal unless they exist. But I still write it this way for you guys because it gives us a checklist to go by instead of worrying about like, because I don't want you to get the idea that like if they both don't exist, then it's continuous there. So they need to exist. And if it is not continuous, if any of these three conditions are violated, we say that it is discontinuous at x equals a. We said it is discontinuous. And if you want to know graphically what it means to be continuous, it means that your graph is connected. And what do I mean by that? I mean that you can trace the curve without ever lifting your pen from the paper, from the page. So you don't ever have to, that's how you know it's connected. If you have the graph of it, if you can continue drawing it with a straight line, you're fine. That would mean that it would be continuous. So I drew 4 different cases here to show you some issues. This is an example, albeit hard to see. Let me zoom in. That'll make it a little bit easier. This was, once again, I got to go back and redo these pictures. I just don't want to. Don't want to have to redo it. That takes time. But anyways, maybe now you can see. This one has an, like, this one is not continuous. Like, yes, I know there's the whole thing where you can, like, you know, there's like the, can you draw the car with a, like this car with, without ever lifting your pen from the page, right? You know, there's that whole thing, like, without over tracing it. Yes, technically speaking, we could draw this whole thing here. We could go, okay, I'm going to draw it, and then I'm just going to stop, and then I'm going to do a circle, and then, yeah, I can do it without lifting my pen from the page, yes. But that's not what that circle is meant to mean. That means that it doesn't exist there. So what would happen is that if I were to draw this, I would draw here. I would have to stop. Thank you for making it into a curve. I appreciate that. I would have to stop, lift my pen from the page, and then continue going. That's how I know it's discontinuous there. Now, what issue is being broken? What of the 3 conditions is being broken there? Yes. Yep, f of c does not exist. f of c does not exist. The limit exists, right? We don't know what the value is, like the graph isn't drawn to scale, so we don't know what that y value is. The limit exists, but the function does not exist there. So the first condition is broken. In fact, also the third condition is broken because you can't have the limit equaling the function if the function doesn't exist there, right? But it is enough to just say f of c does not exist. This one here also discontinues, because if you were to trace it with your curve, you would trace it, you'd have to stop here, lift your pen off the page, then drop it down and go over. What issue is being broken here? The limit does not exist. The function exists, right? There's a solid dot right at the top here, but the limit does not exist. Limit does not exist. The other one, next one down here. The limit, go ahead.
F of C is not equal to.
Exactly right. So part C, the problem is even though the function exists, like we have a solid dot and the limit will exist, they are not in agreement. They don't equal to each other. So that condition is broken. So the limit as x approaches c of f of x does not equal f of c. And I know I said A and now I'm switching to C. I think I made a mistake. And I need to go change these. Then I have to find out. Worst. And then this last one. So there's only three conditions that can be broken, right? Any number of the three. You can break all three, you can break just one. It needs to be at least one. Now here, one might argue, oh, well, the limit and the function don't agree. But remember, the limit is going to be positive infinity, meaning that the limit does not exist. We write that the limit would be infinity, but that it still doesn't exist. Like we write infinity to tell us more about the function, but the limit does not exist. Also the limit, also the function and the limit don't agree. So. Any questions on that? So just to give you some terminology, now I'm not going to test you on this terminology. I'm not going to say like, you have to tell me what these things are, but just so you can bust it out at your next Christmas party and wow your friends and family. Examples A and C, the two on the left column. Those are what we call removable discontinuities. In complex analysis, on the study of complex numbers, we actually call those singularities. So we get to say a removable singularity, which sounds just way more cool. So if you want to use singularity, you can also do that, but we're going to call them discontinuities in this class. And the reason they're called that is because all you would need to do to get rid of the discontinuity would just be to fill in that point, remove that discontinuity, and you've got a continuous function. So that's why it's called a removable discontinuity, because you could remove it and it would be fine. Example B is what we call a jump discontinuity. Because as you can see from the graph, it jumps. It jumps down in this case, or could jump up, whatever, however you want to do. But if it has like a kind of a step in between the two spots, it's called a jump discontinuity. And then if you have an infinite limit, it's called an infinite discontinuity. You will not be tested upon that though. So you can just call it a discontinuity. But if you want to be pedantic, if you want to be over the top, then absolutely. give me the exact name. Any questions on that? Now, one thing that I imagine is on everyone's brain is why? Why are we studying this? What is the point? What is the purpose of continuity? And in general life, nothing. Continuity is very rarely going to affect your daily life. But a lot of mathematical theorems later on, the things that we rely upon in the real world that mathematicians have proved, a lot of them require functions to be continuous. A lot of important implications. One of them, the connectedness of the real number line relies upon continuity. Hand waving a little bit. Compactness of sets relies like through functions. Like basically every proof in like when you start learning about functions later on in mathematics, every proof in function, the problem statement says suppose f is continuous, because if you don't have continuity, a lot of things break down, a lot of things fall apart, sadly. So anyways, we're going to just be using it and examining when things are continuous and versus discontinuous. So does just as a little bit of a reminder, does p of 5 equal 2? No, the limit will equal 2, but the function itself does not equal 2. No. Ooh, wrong color. P of 5 is equal to 4. So the limit as x approaches -4 from the left of p of x. Everyone get a chance to look at it. Don't answer it out loud. What's the limit? 3. Very, very good. So I color code this as we approach 4 from the left. We approach 3. Oh, did it. The limit as x approaches -infinity is going to be positive infinity. As x goes further and further and further to the left, we see that our function just keeps going up and up and up and up. So our y values just keep growing indefinitely. You're free. Yes. So to like I will try to make sure in the future, like normally, like so when I first started writing these notes, just to give you a little bit of like I didn't have an iPad with me. Now I can like bring the PDF onto my iPads that I create for exams and stuff, and then add little arrows and then print it. This one I didn't, but it would be assumed that there's an arrow going up here and an arrow flattening out here. So in the future, on like I think you'll start to see that later on in like in the notes that I started adding arrows. But it is implied, yes. So as x goes to -infinity, this thing just keeps going up and up and up, increasing indefinitely, meaning that the limit is going to be positive infinity. So yes, technically the limit doesn't exist, but we know a little bit more than just saying that it doesn't exist. So find all the values of x for which p is discontinuous. That's the last one. So looking at the graph, read it left to right. Where's the first point of discontinuity? Where's the first x value of discontinuity? -4. It's a jump discontinuity. So we have x equals -4. What else? 0. We have an infinite limit because one side's going to infinity. And we can even actually we're going to do this actually. So at 0, leave a little bit of space because we're going to write things underneath to tell you what condition is being broken. And 5 is another one, yes. Is there one before that? 2 as well. So let's write down what condition is being broken in all 4 cases. And that's the only other one. That's the only other one, right? I don't see any other issues. So with -4, what condition is being broken? So the 3 conditions, once again, the limit needs to exist, the function needs to exist, and they need to be equal. The limit does not exist for the first one. So we're going to write reason or justification. So for -4, the limit as x approaches -4 of f of x does not exist. And that's all we would need to write. So like, it's fairly common, you'll see on quizzes and exams, when they ask you about discontinuity and say, justify why. So it's not enough to just say that it's discontinuous there. Sometimes it's, why is it continuous or why is it discontinuous? It breaks which condition? And that's all you need to write. It is discontinuous at -4 because the limit does not exist. 0. Same thing, the limit does not exist. Limit as x approaches 0 of f of x does not exist. 2. You know, I will be coming down to the bottom. What is the issue with 2? P of 2 does not exist. Very, very good, Chase. P of 2, DNE. And last but not least, what is the issue with 5? Limit exists, 2.
Doesn't jump.
The function exists, it's 4 that at 2, but they don't equal each other. It breaks the last condition. So this one is that the limit as x approaches 5 of p of x does not equal p of 5. That is the issue that breaks the continuity. Any questions on that? Okay. We've been going for about 55 minutes, so I think this is a good time for a little break. Let's come back together again at 10:55. Or 10:05, not 10:55. People watching the recording, go do some jumping jacks, some stretches, whatever. All right, guys, we are back. So now we're going to talk about continuous on an interval. So a function is continuous on an interval. Let's call it I. It could be just like 5 to 7 or whatever. It doesn't matter. But it's continuous on an interval if it is continuous at all values x within the interval. So if you can pick, like, as long as you can pick every x value, it's continuous there, then it is continuous in that interval. If it's continuous on the whole real line, if every x value is continuous, then we'd say that it's continuous everywhere. An important thing, how do you determine continuity analytically? So if you're given the graph, yeah, it's pretty quick to find out. Like, not quick. It can be found without doing too much work. Whereas if you're given the function, if you don't know how to graph it, how would you know where it's continuous without testing every point ever, right? Well, the good news is that polynomials are continuous everywhere. And that makes sense whenever you've drawn a polynomial. If you guys remember that superpower you got, where if I gave you p of x equals, don't write this down, x minus 5 squared times x minus 7 times x plus 4 to the third power. Do you guys remember how you could just graph this just by knowing the zeros? That's superpower. Whenever you drew it, you drew a continuous line. Polynomials are continuous everywhere, and it kind of makes sense. You can plug in, no matter what the value, you can plug it into a polynomial. No matter what the value, like, you can plug in the limit, and they're going to be the same number. But all rational functions, root functions, trigonometric functions, inverse trig functions, exponential functions, logarithmic functions, they are continuous on their domains. So, right? So mainly looking to make sure that we're not taking the square roots of negative numbers, not dividing by 0, not taking the logarithm of a negative number or a 0, right? You can't have log of 0. But exponential functions are continuous everywhere, right? So exponential functions are fine. So it's just on their domain. So we're looking for any of the problems. Just like before, when we were finding domains, you're just looking for the problems that would happen. Same thing here. So with part A, it's polynomial, which means it's continuous everywhere. And I will now start abbreviating continuity or continuous to CONT because it takes way too long to write continuous. Part B, the issue arises that it's a rational function. Its only its domain is all values that would make it so that it doesn't equal 0 in the denominator. So the way we're going to find out is we're going to make sure that x squared minus 1 cannot equal 0, which that factors to x plus 1 times x minus 1 cannot equal 0, which means that x cannot equal 1 or negative 1. Now notice the question though says determine the intervals on which it's continuous. It doesn't tell me to find the points of discontinuity. It's saying find the intervals on which it's continuous. So it is continuous everywhere except for those two x values. Now, if it helps you at first, you can always draw a number line to help you figure it out. So if we were to draw a number line, here's negative 1, here's 1. We pluck these values out, but everything else is fair game. Now, as you get better at this, you don't necessarily need to draw the number line, but if you want to, feel free to. So G is continuous on negative infinity to negative 1 parenthesis union parenthesis negative 1 to 1 parenthesis union parenthesis 1 to positive infinity parenthesis. Can't have x equaling 1 or negative 1. Those are the only issues. Everywhere else is fine. This next one, the log base 3 of x squared minus 2x minus 8. Now, this one's going to go back to nonlinear inequalities because what do we know about logarithms? They have to be positive on the inside. They have to be strictly positive. You cannot have the log, any log, whether it be natural log, log base 3, log base 5 billion, it doesn't matter. Logarithms have to have their insides be strictly positive. So what we need is x squared minus 2x minus 8 to be strictly greater than 0. That will be the domain of this function. And if it's been a while probably, but it's okay if it has been. It's a nonlinear inequality. One side is already 0, that's good. So now we just need to factor the left-hand side. And this factors nicely. It factors to x minus 4 times x minus 2, or plus 2, excuse me, is greater than 0. That gives me the very important points, the VIPs. They're not points, I know, but VIP sounds way better than Viv. Very important values, doesn't have the same ring to it. But the VIPs are x equals 4 and negative 2. So if we were to set up a number line thingy, very technical term. So here is negative 2, here is 4. We'll pick some test values, x equals -3, x equals 0, and x equals 5. And by the way, so what I'm doing here, this is how I figure out solving linear inequalities. I'm sorry, nonlinear inequalities. If this looks completely foreign to you and you've learned a different way, do that way instead. If you don't remember this or you need a refresher, there are videos on this on my on the pre-calculus refreshers. Specifically look for nonlinear inequalities. All right. This is nonlinear inequalities. This is what I'm doing here. So plug in -3, I'll get a negative times a negative, which is a positive. That is a piece that I want because I want my interval. I want my x values to I want my expression to be strictly greater than 0, i.e. want it positive. If I plug in 0, I get a negative times a positive, which is a negative. That's a piece I don't want. And then if I plug in 5, I'll get a positive times a positive, which is a positive. That's the piece I want. So those are the two pieces that solve this inequality, which will be the domain of that function. So h of x is continuous. So h is cont. H is cont on -infinity to -2 parenthesis union 4 to positive infinity. Any questions on that?
What happens if now it became negative?
Say what?
What happens with the negative? You don't include that?
We don't include that because so any number between -2 and 4, the inside would be negative.
This has to be greater than 0.
Yes, because it has to be greater than 0. And if it was negative, it would not be.
And so it's just the whole way?
There's just that entire interval from -2 to 4, it just doesn't exist.
It's like a jump ball.
The logarithm, it actually looks like this, if I remember correctly. So here's 4, here's 2. I believe the function just looks like this. Along that lines. So it just doesn't exist between -2 and 4. Now, K is an interesting case because there's two pieces to it. And we need both of them to be well defined. We need to know the domain of both pieces. Now, for the first piece, we need to make sure that 2x plus 7 has to be greater than or equal to 0. So that means that x has to be greater than or equal to -7/2, which is -3.5 if we want to be exact. Well, -7/2 is the more exact answer, but if we wanted to see it as a decimal, -3.5. So that's one condition that needs to be satisfied, because if we're less than that, even though, so let's just say for the sake of an argument, you looked at -5 or -10 rather. The second piece is defined at -10, right? You can plug in -10 into this function here, but you can't plug it in here, which means you can't plug it into our total function. So we need, first off, from blue, we need to know that the x values need to be greater than or equal to -7/2. And then the second thing is that from here, we need that x cannot equal 5. So if you want to look at it on a number line, to help you figure it out, draw a number line here. Here's -7/2. Here's 5. So from the green, we have that it has to be not equal to 5. And from the blue, we know that it has to be greater than or equal to -7/2. So in total, we have that whole interval from -7/2 to infinity, but we have to pluck out 5. So K is continuous from bracket -7/2 to 5 parenthesis union parenthesis 5 to positive infinity. Any questions on that? How I got that interval? There is something I am actually kind of hand waving here, yes.
Did you just do x minus 5 equals 0 to find the domain of?
Yes, yes. To find for the second piece, I just made sure that the x minus 5 could not equal 0. There's kind of an additional step here. X minus 5, let me. Oop. Grab this, move it down just a smidgen. X minus 5 cannot equal 0. Now, technically speaking, it's interesting that the -7/2 is a bracket on it. I would argue that technically speaking, we need to have a parenthesis there. Because the function doesn't exist to the left of -7/2. So you can't actually test the limit there, right? Remember we were talking about that way back when we had like, I think it was the limits as x approaches 4 from the left, or 4 from the 4 from the left of the square root of 4 minus x squared. 60. No, it was limit as x approaches 2 from the left. We had this thing here, and it worked on the left-hand side, but on the right-hand side, it didn't exist. Remember that? From section 1.3. So technically speaking, the full limit won't exist at -7/2, which would argue that we should have a parenthesis there instead of a bracket. And that gets into a concept that we will call, that is called continuous from the left and continuous from the right, which we will not get into. So I would accept either answer on a quiz or an exam. If this was the question on the exam and I asked you for where it's continuous and you wrote this, I would give you full credit. And if you wrote a parenthesis instead of a bracket on that -7/2, I would still give full credit because that is a advanced math topic that we don't need to worry about. For us, just find its domain. That is where it's continuous. Any questions on that?
No.
Okay. So we get to one of the more fun things, in my opinion, which is finding continuity of piecewise functions. Because these are the ones that kind of cause the most issues. Because there is a surefire way to do it, and that would be to graph it. But sometimes that can be a little more tedious than not. So I've kind of developed a step-by-step process that I hope you can follow along with. Imagine what it means to be a piecewise function. It means that on given designated intervals, in this case, when x is greater than 0, you're the first function. When x is less than 0, you're the second function. On those pieces, we're defined as that function. So step 1 is going to be find the discontinuities on each piece. Find the discontinuities. Sorry, I wanted to write it a little bit better. Find the discontinuities of each function piece on its designated interval. On its designated interval. So it's not just another. So what we're going to do is we're going to start off by finding each piece's discontinuities. So in the example, we have two pieces. For x greater than or equal to 0, f of x, let's not write, we'll say y equals 10 over x plus 1 times x minus 2. Right? When our x values are greater than or equal to 0, our function is the top piece. Where is that thing discontinuous? -1 and 2. That's correct. So discontinuous at x equals -1 and 2. However, one of these ones is not actually a place of discontinuity. Where is it? -1. Derek says that -1 is not actually discontinuity. And he's right. Why? Exactly right. Exactly right. Capri is exactly right. So this is out because we are only defined as this function for x greater than or equal to 0. So as we are only defined as this function, this first one, for a value is greater than or equal to 0, yes, the actual function, y equals 10 over x plus 1 times x minus 2. If I was asking you that, where that thing is discontinuous, you would just say -1 and 2. But we are only concerned with this function when x values are greater than or equal to 0. So that -1 isn't a problem for us. And if you were to graph this function in Desmos or something, if you were to graph this piecewise function, you'd see that that part of the graph isn't there. So it's not a problem that we have to deal with. So we only get 2 from the first piece. For x less than 0, y is going to equal x minus 5, right? Discontinuity is that. Nothing. It's a line. It's a polynomial. It's one of the more boring examples of a polynomial, but a polynomial nonetheless. And polynomials are continuous everywhere. So this one has no discontinuities. So my recommendation when you're doing it this way, I like to do this in a step-by-step procedure, and I hope the way, like, we're going to rehammer it out afterward. But what I would recommend is after you've done step 1, write down the discontinuities at the very bottom of it and then move on. So you have a finite spot to look for instead of having to trace back through all of your work. So after doing step 1, we found out, so from step 1, discontinuous, so discont at x equals 2. This is just going to allow us to find it once we've done the whole thing. Does that make sense? When I, like, another example is when I'm solving systems of equations, like a 2x2 system or a 3x3 system, I always underline my answers as I go along so that I don't have to parse through all of my work to find out where my answer was. This is one of my issues. So that's step 1. Any questions on step 1? Yes. So it was only a problem for the top function. It was only a problem for that. But our function isn't so yes, -1, x equals -1 is in the second piece's domain, but the second piece it doesn't have a problem in -1. So we don't need to worry about it. If this had instead, so here's a good thing. If the function was defined instead as this, x greater than or equal to -2 and x less than -2, then both values would be problems, because -1 would then be in the first piece's designated area.
The -1 is not included in a restriction.
Yes, as it stands right now, like with the original function, it's not there, so it's not a problem. But if the bounds of the piecewise function were changed to what I have right here, greater than or equal to -2, then it would be an issue. Does that help? All right. Any other ones? You guys are awesome, asking excellent questions, guys. I love it. Love it. My favorite part. So, step 2. Now I want you to like, let me not underline that. 'Cause then my underline doesn't look great. What would you think would be the next step? We've checked the pieces. What else do we need to check? There are values that divide the interval and divide it into two different functions. If we go back to this curve that we drew here, that we have here, it's several different pieces, and between pieces it can jump. So we need to check the dividing values. So determine if discontinuous at dividing values. You'll need to do left and right hand limits. So, just as a reminder from the very beginning of the section, the three things that are required for continuity: the limit needs to exist, the function needs to exist, and they need to be equal. So we're going to check the limit, but that's not enough. And we remember from section 1.3 that when it comes to piecewise functions, if you're talking about a dividing value, on one side of that, it'll be one function, on the other side, it'll be a different function. So, in the example, we have one dividing value, 0. That's our only dividing value, and they usually come in an odd number. So in the next example here, I don't know if I'll have time to do it. I might just post a video of going through this one later on for you to watch. But this one has 3 dividing values, or sorry, no, 2. I'm done. I can't count. What do you expect? I'm not a math major. There's like 2 dividing values, but I digress. This one only has 1 dividing value, and that is 0. So for 0, for x equals 0, we need to check. So condition 1. F of 0. We need to find f of 0 because, and so this is an important thing. This is an important thing. So going back to it, which function would I plug it into? First one, that's right. Because the first one is the one that's defined for x values greater than or equal to 0. So f of 0 equals 10 divided by 0 plus 1 times 0 minus 2. That'll be 10 divided by -2, or -5. So f of 0 exists. Now I'll explain why we still need to check condition 1. A lot of students will make the mistake of just checking condition 2, i.e. the limit, and then saying it's good, because most of the time that's enough. But you'll see why we need to do it once I talk about it. Condition 2. We have to check the limit. Now, sadly for us, this is a dividing value. Not sadly, happily, because we love taking limits. Limits are fun. And it's one of the things that you guys as calculus students now get to do. You guys all know your own limits now. That's a good thing to know, is to know your limits. Yes.
When you plug in the 0, you're just checking if 0 just works.
Yeah, we're just checking to see that f of 0
But
exists.
this applies to all the other columns. It's like with x equals -2, you plug in -2, just how that works.
And so you see that, like, if you try and do that, if you try and plug in 2 here, you'll see that it gives you does not exist, meaning that it's discontinuous there because f of 2 does not exist. So the limit as x approaches 0 from the right of f of x, what function would we be? Number 1, I'm going to label them 1 and 2. 1 and 2. if x is approaching 0 from the, did I say left and I wrote the right? Yeah, I meant to say, if I'm approaching 0 from the right, which function am I using, 1 or 2? 1, first one. So I get to rewrite f of x as what it would be there. It's the limit as x approaches 0 from the right of 10 over x plus 1 times x minus 2. And because this won't cause any issues, right? When we were doing limits, in general, we look to make sure that we're not going to be like dividing by 0, taking the square root of negative number, all that stuff. And plugging in 0 isn't going to cause any issues, right? If there was an additional x here or something, that would cause issues. But as it stands, we're fine. So we can just plug it in. 10 divided by 0 plus 1 times 0 minus 2 equals -5. Yes, I know it's the same calculation that we did in condition 1, but the concept is different. Here we're checking the function value. Here we're checking the limit. So right-hand side existed. The limit as x approaches 0 from the left of f of x, that'll be the secondary function because we're approaching it for values less than 0. So this will be the limit as x approaches 0 from the left of x minus 5. Once again, a function that doesn't have any problems. It's a polynomial. Shouldn't have any issues plugging this in. So we just do that. 0 minus 5 equals -5. So the limit exists, right? And equals -5. Because the left and the right hand limits agreed. Let me say that one more time. Equal, which implies that the limit as x approaches 0 of f of x equals -5. Sadly, we're running out of room here. My handwriting got too big. Because there's one last step. To reiterate, so the limit from the right of 0 equal -5, the limit from the left of 0 equal -5, meaning they gave us the same value, which means that the limit itself exists and is also equal to -5. So limit as x approaches 0 of f of x exists. And condition 3 is vacuously satisfied. Condition 3. F of 0 equals -5, which equals the limit as x approaches 0 of f of x. That is satisfied. The limit and the function equal each other there. So it is not discontinuous. It is continuous there. Continuous at x equals 0. So no discontinuities from step 2. Sometimes you will. If you get to the, like, usually speaking, I would check condition 2 first. Because if condition 2 breaks, condition 1 is almost always going to break. Condition 1 is not going to be needed. With piecewise functions, the limit is the most important one. But I want to show you all 3 conditions working. And then I'm going to add in an extra page. Unfortunately, I just wrote too big. Add in a page. There we go. So step 3, sorry about that. Is to use step 1 and 2 to create the interval. Because this question was asking for the interval on which it's continuous. If it was asking for where it's discontinuous, we would just write 2. But it's asking for where it's continuous. So in the example, only one discontinuity at x equals 2. So that is the only issue. 0 wasn't an issue. -1 was an issue, so that was the only one. So that means that everything else, so from negative infinity up to 2 is fine. 2 to infinity, fine, but not including 2. You could draw a number line. So f, right? F was the name of this function. F is continuous on negative infinity to 2, parenthesis, union 2 to positive infinity. Any questions on that? It won't be a bracket because bracket would mean that it would be included, but we can't include 2. Oh, sorry, let me get rid of the page thing. That's unnecessary. So why did I have you check condition 1? Even though like we basically did the exact same calculation in condition 2. Because what if I had been a stinker and instead of writing x greater than or equal to 0, what if I had written this? Then the function wouldn't exist at 0, right? The function wouldn't exist at 0, so it would have to be a discontinuity because there'd be an open circle there. Yes, the limit would exist and it would be -5, but if I wrote that x had to be strictly greater than 0, then the function wouldn't exist there, meaning there would be a discontinuity. So you do have to check, you do have to actually plug in the value. It's tedious, I know, but it is important. Any questions on that? All right. I don't think we'll be able to get to this. Like, so we got time. I'm not calling it early. I'll post a video of this one, recording that, or we'll do it on Wednesday. I'll determine how much time we have. But the answer to this one will be soon. If you'd like to do it yourself, please do so. I encourage you. Just do it on some scratch paper. And we'll get it done at some other point. But I wanted to go over the next 2 examples because they're really fun. So find a constant k such that the function below is continuous everywhere. F of x is equal to k e to the x plus 2 when x is greater than or equal to 1, and 2x plus 1 when x less than 1. So the issue there, what do I need to do? Well, we need this function to be continuous. So let's look at each piece, right? Step 1. On each piece, we have continuous functions. So no discontinuities from the pieces themselves, but from the function pieces. Now let me elaborate once you've written that down. When x is less than 1, we're 2x plus 1. That's a line that is defined everywhere. So it's fine. When x is greater than or equal to 1, you are k e to the x plus 2, where k is some constant. Could be 5, could be 6 billion. We don't know, but it's just a number. And e to the x is defined everywhere. Like the domain of e to the x is everything. So that function has no issues. It's just we don't know what k is. Does that make sense? So k is a problem, but not for step 1. Step 2. Step 2 is where it comes into play. We need the left and right-hand limits to be equal. at x equals 1. Right? That is how we're going to find out what k is. That is going to be how we figure this problem out, because in order for this function to exist, in order for this function to be continuous, we need that the limit at x equals 1 has to exist. And the only way that's going to happen is if the left and the right hand limits are equal. So let's just go ahead and start doing that. This is an example of what I like to call following your nose, right? Channeling your inner toucan Sam here, busting out your colored beak and figuring out, just following it to the flavors of fruit wherever they grow, you know, the whole thing. Anyways, so let's check out the left and the right hand limits. So limit as x approaches 1 from the right of f of x. Which function would I be? 1, the part 1, yes. So say 1 and 2. The reason why, I will concede. The reason why I'm being very particular and asking which function is to be careful. I usually like to make mine go greater than and then go down. Like I start with a greater than and I go down, but some textbooks like to start with a less than and then go down and then go up. So it's always important to be very, very careful when you're reading a problem to make sure you know which piece is being defined at which interval. So you'll be piece 1, which would mean you'd be the limit as x approaches 1 from the right of k e to the x plus 2. Oh no, I don't know what to do. I've got 2 variables. I'm scared. It's fair to be scared, right? It's 2 variables. We're talking about single variable calculus right now. But the fact of the matter is, remember, this is a limit as x approaches 1. So in the limit's eyes, that k is just a constant. It doesn't matter. So we can just take the limit of this because e, you can just plug in values into e. E doesn't have anything where you're dividing by 0 or anything like that. So we'll just plug in the value for x. K is just treated as a constant in its eyes. So this becomes k e to the first power plus 2. Or just k times e plus 2. Remember, e is just a number. E is a number like 7 or whatever. E is 2.714-ish. Or 2.71-ish. I think, I can't remember if it's 14 or 18. I can't remember off the top of my head. I should know. E to the first power. What is e? 2.718, not 7.4. Unacceptable. I should know. So 2.718. It's just a number. And limit as x approaches 1 from the left of f of x is going to equal the limit as x approaches 1 from the left of the second function, 2x plus 1. And much like the first one, that is a very, very nice expression. 2x plus 1 has no issues. So we can just plug in the limit. This is going to be 2 times 1 plus 1. That's going to be 3. So in order for this thing to exist, in order for the limit to exist, we need these 2 things equal. We need these equal. If they weren't equal, then the limit would not exist at large. And if the limit doesn't exist, then it's not continuous. So that's a way for us to solve for k. So we have ke plus 2 is equal to 3. That means that k times e is equal to 1, which means that k is equal to 1 over e. E is just a number. So we can divide by e. E is just a number. So we could say, like, I heard someone say, we can do that. And it just reminded me of one of my most eccentric teachers at University of Washington. We were like in my senior year. This guy was a super all mathematicians are weird. I'll say that much. All of us are weird people. But like he would wear like sparkly gold shoes. They're like bright sparkly gold. And just he was super weird. But I remember we couldn't figure out a homework problem, and so we asked him in class, like, can you please go over this? We don't know how to do it. And so he did it, and he was like, so then we're just gonna do this. We're gonna claim that this is true. He's like, we're gonna do this. And then one of the students said, can you do that? And like just deadpan face said, I can do whatever I want. Like to be fair, the guy was like big in like he was a big name in mathematics, at least in his field of topology. So like he had that confidence in him. But like I just love the idea of saying I can do whatever I want in mathematics. I'm a mathematician. So yes, I can. Can we do this? Yes, I can do whatever I want in mathematics. So yeah, E is just a number. It would be no different than seeing it as K times 2 plus let's not use 2. We've already used it a bunch. K times 7 plus 2 is equal to 3. Subtract 2, 7K is equal to 1. So K is equal to 1/7. No different than that. So, anywho, we don't have enough time to go over the next one, but the next one is just as fun. And we'll finish off with that one next time. Don't worry about the intermediate value theorem. I'm not going to test you on it. It's just a fun little useful tool that useful quote unquote. So that's what we'll leave off. So we have our next quiz. I'll email you guys tomorrow about the sections that are covered, but it's also mentioned on our calendar, which is found on the bottom page of our bottom of our homepage. If you guys have any questions, feel free to email me. Otherwise, you guys have a great rest of your day, and I will see you guys on Wednesday.